I'd like to talk today about another special type of distribution. Just like we've talked about the binomial distribution in class, there's another special distribution called the geometric distribution. So let's put the date up here at the top, and let's talk about what a geometric distribution is. So I want to consider just the geometric setting. We have bins that we talk about with our binomial distribution in order to figure out if we're in the right setting for a binomial distribution. So I'm just going to use a little sentence here. Let's talk about the setup, what needs to happen in order for this to be a geometric distribution. So we are going to perform independent. And of course, with independence, we could be told potentially that it's independent. We could have replacement that would satisfy the independence, or we can still use that 10% rule to get the independence condition to be met. So we want these to be independent trials of some chance process. And we are going to record the number of trials it takes to get one success. So this is different from our binomial distribution in the fact that we don't have a fixed set of trials. I'm going to continue this process forever and ever and ever until I get one success. So I'm going to raise you an example here. Let's say that my car is dead in the high school parking lot, and so I'm going to need someone to jump my car. Well, I could stop people on their way out of the parking lot and ask them, hey, do you have a jumper cable? And if they say, yes, that's great, I can be done. I'm not going to keep asking people for more jumper cables because I only need one. So I don't know how many people I'm going to have to stop, but eventually I know I will find someone with a jumper cable and then I can stop this process. That would be an example of a geometric. We also, the first thing we talked about with binomial distributions, when we were on page 27, we looked at example C. So if you want to flip back to page 27, example C, shuffling a deck of cards and repeating until we get an ace. That is a geometric distribution, which I mentioned when we did the notes, and then now you can understand what that means. So in this case, we're going to have a variable, and let's call it y. Y is going to be our random variable, and y is always equal to the number of times it takes to get one success. Always. And it's always one success. It doesn't have to be y, but I'm just using y for this example. But if we're having a geometric distribution here, we want to continue this process until we get one success. So to define the geometric probability, we will know that y is distributed geometrically, and we can just put geom with probability of success p. Unlike the binomial distribution, we don't need to say what n is because we actually don't know what the number of trials is before we start our process. And the formula that we're going to use, we want the probability that y is equal to some number of trials it's going to take, and that y equal to k. Well, in order for this to happen, I need to have a bunch of failures in a row. I hit a bunch of people who do not have jumper cables in the parking lot. Eventually, I will get that one person that does have jumper cables. So it's very similar to our formula for our binomial distribution, but I'm going to put the successes first. I'm sorry, the failures first. 1 minus p is the probability of failure. And I have 1 minus p to the power of k minus 1, because it's going to take me k tries to get a person with a jumper cable. So k minus 1 times, I will have a person with no jumper cables. And then the very last time, I will find someone who does have jumper cables, p. Let's look at one example here. I would like you to read this question at hand, and then we're going to answer the questions here. So go ahead, pause the video, and read the example here about the Lucky Day game. All right, y is going to be equal to the number of picks, or in this case, it's the number of homework problems. Because you're going to continue and continue and continue until you match the lucky day. Let's find the probability that you get exactly 10 homework problems. So for part A, we're looking for the probability that y is exactly equal to 10. And in that case, I need to fail 9 times and succeed once. So I fail 6 out of 7 times with a 6 out of 7 probability, and that needs to happen 9 times. And then I need to succeed with the 1/7 chance as the very last one. And let's see what this is if you plug that into your calculator. All right, so let's look at number B. B is asking me for the probability that y is less than 10. So let's think about what this means first. This is going to be that the number of homework problems is strictly less than 10. Now remember, your teacher is planning on giving you 10 homework problems. So if you play this game, the goal is to have less than 10 homework problems. So let's see the probability that you would get less than 10 homework problems. We have to consider a lot of options here. So let's write down all of the different possibilities that y could take. That's a lot of things. This is a discrete random variable, more specifically the geometric random variable. And actually, you know what we should have done too? We should have put at the beginning that y is distributed geometrically with a probability of success of 1/7. So let me make sure that I have that on there. We have a lot of things that we need to add together. Now there is a way to do this in your calculator. So what I'm going to ask you to do is at the very bottom of this page, it mentions to look at pages 406 to 407 to find the probability in your calculator. Those are going to be in your book. So, and I'll ask you, we're in chapter 6, so open up the chapter 6 book problems, read those 2 pages about finding geometric probabilities. And what I'll do is I'll just put the formula on here. So if I'm going to have y equal to 1, that means I succeed on the first try, I get 1/7. If I have y equal to 2, that means I fail on the first try, but I succeed on the second try. Y equals to 3 means I have to fail twice and succeed the third time, etc., etc. And we'll follow kind of the same formula until the end. The last one down there is y equal to 9. So I need to fail 7 times and then succeed the very last time. You can absolutely write out all of those middle terms that I omitted, multiply and add. That's going to be a lot of work and a lot of room for error. My recommendation for you is to look at this, the thing in your notes about finding the geometric probability, and I'm going to ask you the Edpuzzle question to tell me this probability. So you either have to choose, you have to either type everything in or go read about how to find it in your calculator, and then I can answer any questions that you have about finding the calculator when we get back to class. And there's my answer for the geometric probability. Let's go ahead and interpret it. I'll ask you another Edpuzzle question about the interpretation, and then I'll put my answer here. There you go. There's my answer up there on your page. Let's write down the formula for the expected value. And I do want to make a note here that this formula is not on your formula sheet. So this is something that you are going to want to remember. And we'll use mu of y since y is our random variable. It's the same as the expected value of y, and that's equal to 1/p. So in words, you could say this is going to be the expected number of trials to get 1 success. Remember that y is always defined as the number of trials. So the expected value of y is going to be the expected number of trials.